Whole of physics class. I'm Andy, Caleb's right there, and then behind the camera is Justin. So we got number 5. What is the electrical potential at D equals 15 centimeters along the x-axis from a rod of length 11? So there you go. Charge is 33 nanocoulombs. What did I say, 33?
Yep.
Cool, there you go. So you have this rod, right? And for some reason we're interested in the electric potential right here. So we want V. Well, you get this one from the book. I probably skipped like 6 steps. That's fine. So we wanted to know from here to here, right? So this is line of arbitrariness, x. So what is the voltage difference from this point charge, or this, this little bit of charge all the way to here, right? You have this differential bit of length right here. That's why I have the integral, right? dq. That's not Dairy Queen either. So we're going to set this up as x plus r, because here's x, r is going to be this length right there, from dq all the way to d. We're going to integrate that with respect to x, and we come up with kq over l, natural log of something, r plus l over r. If you've ever had Brother Brown in mathematics, he would always say, it turns out that V equals, what is it again? 356.4 point something something volts. And that's the answer. That's how you do it.
Perfect. So just to kind of clarify how he got to this point, if you're really interested, I can show you how to do that real quick. And we know that V, and this is from the equation sheet, V is equal to KQ over R. And we also know that lambda is equal to Q over L. And we can call it, in this we can say that that's equal to the integral of K dQ over R. And we can say that dQ is equal to lambda dx, and that really just comes from this formula over here. Instead of using L, we'll use dx. We call this dq and we solve for dq. And then if we go ahead and plug q over L back into lambda, then we have that dq is equal to q over L dx. And so once we have that, we go ahead and plug that back into this equation, and we get this part right here. And then he went ahead and showed you how to get that. If we're to do unit analysis on this, it's pretty simple. All we have to do is, we know that K is in Newton meters squared per Coulomb squared. And then Q is coulombs. And then L is in meters. And if we come up here, dx is also meters. And x plus r will also be in meters. So if we go ahead and cancel things out, we have 1 coulomb that cancels, we have 2 meters on the bottom that cancel with the meters squared, and then we have Newton meters per coulomb, and we know that a Newton meter is a joule, so it's a joule over a coulomb, which is equivalent to a volt. And I'm pretty sure you can't see that, but it is in volts, and that's your final answer.